Hi you guys, and welcome back to my channel. So today we're going to be talking about solving nonlinear systems, and this includes equations and inequalities. Let's jump in. So let's take a look at what a nonlinear system of equations would look like compared to a linear system. So our first case, our nonlinear system, would be x squared plus y squared equals 4 and 4x squared plus y squared equals 36. What makes this system nonlinear? Well, you can tell that the power of both the x and the y is 2, so this would not be a line when you graphed it. So simple as that. Linear means involving a line. So if we compare our nonlinear to our linear system is two equations that are both lines versus nonlinear, one or more of the equations is not a line. So when we look at solving these, just like we've learned with our other systems, we can solve them both algebraically and graphically, but the more equations you get in your system, the better it is to go with an algebraic approach. So we're going to focus on an algebraic approach. Let's solve the following nonlinear systems algebraically, and then we'll go ahead and check graphically. Okay, so our first example, we're going to go ahead and solve the system. X squared plus y squared equals 4, and 4x squared plus 9y squared equals 36. Okay, so when we approach these algebraically, we could go with either an elimination or a substitution strategy. It looks like for this system, a substitution-based strategy would be as easy as anything. So we can notice that our first equation, it's pretty easy to solve for either x squared or y squared. Let's go ahead and solve for x squared. So x squared would be equal to 4 minus y squared. And then we can go ahead and substitute that in to our second equation. Okay, so then that goes in for our x squared. 4 times 4 minus y squared plus 9y squared equals 36. And we can distribute that 4. And we'll go ahead and combine like terms. So we get 16 minus 4y squared plus 9y squared is 36. Combining our y squared terms, we get 16 plus 5y squared. And then we can solve this equation for y pretty easily with just algebra. Some of these quadratics, you might need to use the quadratic formula or factoring, something like that. But for this one, pretty easy. So dividing both sides by 5, we get that y squared equals 4. And that means our two solutions would be plus or minus 2. Okay, and notice the second to last step. I'll highlight the fact that the square root of y squared is actually the absolute value of 4, or actually the absolute value of y. And definitely it's one of those steps that a lot of algebra teachers leave out, especially if you're in a beginning algebra course. So you might have just seen this entire second to last line skipped, in which case your teacher would just say plus or minus 2. And hopefully it's easy to see when you plug those back into the equation why they would both be solutions. So our two solutions are y equals plus or minus 2. Now, keeping this straight, that means that there are probably going to be at least 2 points of intersection here, right? Because our y is 2, we'll go with some x values, and our y equals negative 2, we'll go with some x values. So we're going to keep them straight, and now we're going to take y equals 2 and then find x values. And we'll take y equals negative 2, and we'll find those x values. So two separate things. Okay, so going back to our original equation, we can substitute in that x squared plus 2 squared equals 4. We get x squared plus 4 equals 4. So then looks like we'll only get one solution, which is that x would have to equal 0. And when we go back and plug that in, plug that negative 2 into our first equation, we'll get x squared plus 4 equals 4, and we'll get again that x can only equal 0. Okay, so let's keep track of our points. We found 0, 2, and we found 0, -2 as our proposed solutions. So we'll go ahead and check those graphically. Now, when I say check those graphically, we want to take a look at our picture and make sure that it makes sense on the graph, that we're not missing anything, that we didn't make any sort of mistakes. So when we look at the graph of these two equations, you might want to think back to our systems. What does the solution represent? It represents the intersection of those two curves on the graph. So I'm expecting to see two intersections when I graph these. And we'll do a quick hand sketch because these are conics that we're familiar with, but we can verify with technology. So x squared plus y squared equals 4 is a circle with radius 2. Doing our best with the scale here. So there's our circle with radius 2. Just our scale so it's a little bit more accurate. There we go. And the next curve, our second curve, let's do that one in red. So that one would be, looks like an ellipse. And let's remind ourselves what the standard form of that would be. If we divide both sides by 36, we'll get x squared over 9 plus y squared over 4 is 1. And we can see that our distance from the center of the ellipse, which is 0, 0, to the point on the curve will be 3 in the x direction. So from the center we count 3 out. 1, 2, 3. And then in the y direction we count 2. Okay, so lining up perfectly with the circle there and connecting our ellipse. Okay, and you guys can tell what are our actual solutions to the equation. We'll star those. The solutions are the intersection points, and we can see clearly that because the ellipse is actually containing the circle except for those two intersection points, we're only going to have 0, 2, and 0, -2. So it checks out. Okay, so once again, our solutions are the intersection points 0, 2, and 0, -2. Nice. Okay, so let's go on and check out another example. For example B, our system will be x squared plus y squared equals 4, and 4x squared minus 9y squared equals 36. And taking a look at what kind of curves we're looking at, we just saw x squared plus y squared equals 4, which is a circle, and it looks like our second curve is going to be a hyperbola. So why would it be a hyperbola? There's a minus there between the x squared and the y squared terms. Okay, so let's jump in. We'll use substitution again. We know that x squared equals 4 minus y squared. And we can go ahead and substitute into our second equation our value for x squared. We get 4 times 4 minus y squared minus 9. Y squared equals 36. So 16 minus 4y squared minus 9y squared equals 36. And then combining like terms, we get 16 minus 13y squared equals 36. Okay, so we're going to get some interesting values here. So negative 13y squared. Okay, so y squared equals negative 20 over 13. Okay, with this as the point, let's take a look at what this would mean conceptually. So if our y squared value is supposedly negative, when we try and square root this, we're going to get no real solutions for y, because when we square root a negative, we get a complex value. So this would imply there are no real solutions. Okay, so if there are no real solutions for y here, what that would mean is that there are no intersection points. Okay, I can already tell if I have no y coordinates that are solutions to this system, then there can't be any intersection points. So we'll take a look at the graph and we'll make sure that that's actually accurate. Okay, so x squared plus y squared equals 4 is our circle with 2. There we go. And our hyperbola, when we put that into standard form, would be x squared dividing both sides by 36. We'd get x squared over 9 minus y squared over 4 equal to 1. So graphing our hyperbola, remember, is a little bit more challenging than graphing our ellipse. We need to come up with our viewing rectangle, as I like to call it. So this hyperbola will be centered at 0, 0. Because there's no x minus h squared or y minus k squared. So that means our h and k are 0. And then counting out 3 in the x direction. And 2 in the y direction. Here's our rectangle. Okay, and using that rectangle, we can form the diagonals of this. And here's our asymptotes. Okay, and recalling that a hyperbola is going to open along the direction of the dominant term. So the dominant term is the x squared term, so that would mean that this is a horizontal parabola. So it's going to open up along the left and right, like so. Okay, so now is a good time to recall what is actually part of the hyperbola and what is not part of the hyperbola. So even though it's easy to graph the asymptotes with solid lines and see them, just remind yourself that the asymptotes are actually not part of the curve. So when we finalize our sketch, the asymptotes, we should probably leave those dotted, because the asymptotes are where the curve is not. So the asymptotes are not part of the hyperbola, nor is the dotted viewing rectangle part of the hyperbola. The only part of the hyperbola, let's highlight that in blue, would be these two branches here. Okay, so now we can very easily see why we would get no solutions here. Our circle and our blue branches of the hyperbola are completely separate. So this sketch does in fact confirm that there are no intersections. Okay, so this would be an example of what a no solution would look like on one of these nonlinear systems. Very similar to what it would mean with lines. It's just that we can get no solution a lot easier when you're not dealing with lines. Okay, let's take a look at solving nonlinear systems of inequalities. So with nonlinear systems of inequalities, we're still going to be dealing with things that are not lines, but the only difference is obviously instead of equations, we're dealing with inequalities, and hopefully that's pretty easy to see right away that we will be dealing with an inequality. So I want to remind you of what we did when we were solving linear systems of inequalities. Linear systems of inequalities are the kind of systems where you would have two lines and you would be shading on different sides of the lines depending on the solution. So when we get our solution set to these, we're going to have a shaded region. And the reason why is there's going to be infinite solutions. And there's really no easier way to describe the solution set than with a picture showing those shaded regions of infinite solution. And that's just a possibility, not saying that that's going to happen every single time, but a majority of the time it will be an entire shaded region. Of course, we can also have a no solution We can also have perhaps a single, yeah, it's possible for there to be a single point solution. Okay, so let's dive in. So for example A, our first example, we're looking at the system of inequalities, x squared plus y squared greater than or equal to 4, x squared minus 2x plus y squared minus 2y less than or equal to 0. Okay, so taking a look at that first system, how we're going to do this is we will be graphing these, obviously, but we want to make sure to take care to graph the equality part. So we'll graph the curve first, just like we were graphing an equation, and then we'll shade whichever part of the solution is, whichever part of the graph is a solution to that inequality. So let's take a look at graphing x squared plus y squared equals 4. Okay, we already saw that is a circle. Okay, there's our circle. And now we're going to check, is it solid or dotted? So with an inequality, if your curve is or equal to, we graph those as solid curves, and if it's just a strict inequality, then the curve itself would not be a solution to that inequality, so we'd leave it dotted. So in this particular case, it is solid because of the or equal to. Okay, so check on that one. And then we're going to graph the next curve. Actually, let's shade before we graph the next curve. I think this is how most people prefer to do it. Okay, so we're going to shade the solution to that first inequality. We're looking for the x and y values that will plug in and make it greater than or equal to 4. So what we want to think of is inside the circle versus outside the circle when we're shading this. So next we'll shade. Okay, so all the points on the inside or outside will share the behavior of either making the inequality true or false with these. So we only have to check one point, and we'll just check 0, 0, because we know that's clearly inside. So with 0, 0, is it true that 0 squared plus 0 squared is greater than or equal to 4? It is not. False. So we got that the point on the inside is false. That means that the points inside this circle will not be solutions. So when I shade, I'm going to shade only outside the circle. Okay, so the shading represents all the points that are solutions to the first inequality only. Okay, now we'll go ahead and graph the second inequality following those same steps. So our second inequality looks like we're going to have a circle. So let's get our circle into a more standard form. I can tell it's a circle because I've seen a lot of these and I know the patterns. I can see that the x squared and y squared terms are both positive and they don't have different coefficients. So I can tell right away this is going to be a circle of some sort, and we'll just have to see what its standard form is. So to get it in standard form, we complete the square. We get x minus 1 squared minus 1, and we get y minus 1 squared minus 1 after completing the square. You might want to check out at this point my video on how to complete the square on these. I did that kind of quickly. So adding 2 to both sides to get rid of the negative 2. We'll get x minus 1 squared plus y minus 1 squared equals 2. So our center is 1, 1, and our radius is square root of 2. Okay, so we're definitely inside of our other circle. Let's color code this. We're going to graph this one in red. Okay, so if our center is 1, 1, need to be here. And then our radius is square root of 2, so about 1.5. Okay, and it looks like we have a couple of intersection points between them, but when we're graphing these, we're not trying to find only the intersection points. Remember, we're trying to find all the points that solve the system. So when we shade is when we're going to get our full solution. So let's check, is this one supposed to be solid or dotted? It looks like we have an or equal to, so it's supposed to be solid. And then we need to figure out, are we going to shade inside or outside? So let's check with the point. Something that's obviously inside would be our center, 1, 1. So when I plug in 1, 1 to my curve, 1 squared minus 2 times 1 plus 1 squared minus 2 times 1. We want to see, is that less than or equal to 0? So I get 1 minus 2 plus 1 minus 2. So it looks like it would be negative 4 plus 2. So it would be negative 2. And is that less than or equal to 0? Yes, it is. Okay, so that means we would be shading inside the circle. And we'll shade that in red. Okay, so now I'm going to look for the solution to the system. It's going to be the points that are shaded true for both of the solution sets to the individual inequalities. So the solution to the system is the double shaded region. Let's go ahead and really make that solid to highlight it. It looks like it's going to be this little crescent half moon shape in here. Okay, so the part that's outside the black circle and inside the red circle would be our solution set. And we'll just make a note that the solution set is what's double shaded. So when I look at students' work on solving these, this is all I would need to see is this picture, doing your best to make the graph as accurate, and then showing your shading clearly. I prefer to see students do it in different colors, and I think it's easier for you to see if you do it in different colors. But if you don't have different colors, you can always use different shading techniques to help you out. Okay, so let's check out another example. Okay, so our exercise part B was y squared minus 4 less than or equal to x less than y plus 2. So this one's written kind of interestingly because at first it might not appear that it's actually a solution or actually a system, but you can actually see that it is a solution because this is a compound inequality. We have two different conditions that must be true. So our two conditions that must be true is the first inequality, y squared minus 4 less than or equal to x. And the second one would be x less than y plus 2. So let's write it that way. Y squared minus 4 less than or equal to x, and x less than y plus 2. Okay, that is our system, a little bit more familiar as how we've seen it. And if I look at what this would actually be, it looks like the first one would be a parabola. Looks like it's going to be a sleeping parabola, and then the second one looks like it's going to be a line. So I might want to write these a little bit more. I guess the first one's about how I would graph it, and the second one, I would probably rewrite this line as y equals mx plus b. So I'd probably move the 2 over and write this as y greater than x minus 2. Make sure you just pay attention to the direction of the inequality. Okay, so there's our system. And let's take a look at graphing it. So when I graph my sleeping parabola, it looks like the vertex for this will be at -4, 0. And let's get 2 more points on this parabola. So looks like the y-intercept on this would be +2 and -2. My scale's a little off here. Okay, and let's check in with whether this is supposed to be solid or dotted. It looks like it's supposed to be solid because of the or equals to right here. And then let's graph our line. Actually, let's shade. So let's shade in black the solution to this inequality. And again, we're going to be thinking inside the parabola versus outside the parabola. So a point that's clearly inside the parabola that I think would be easy, it would be 0, 0. So let's check 0, 0. If we plug in 0 squared minus 4, is that less than or equal to 0? And it definitely is. So it looks like we're shading inside the parabola here. Leave the shading open, and then we'll get it more solid when we see where our actual solution set is. Okay, so there's our solution to the first inequality, and then we'll look at the solution to the second inequality. So our second curve would be a line with y-intercept -2, and it looks like it's positive slope 1. Okay, so there's our line. And it looks like this one is an example of a curve that should be dotted because the inequality would imply that points that are actually on this curve would not be solutions because that would be y equals x minus 2. So we'll just make it dotted here. Okay. And then we're going to be looking at shading. Are we to the left of the line or to the right of the line? So let's look at an easy point to visualize. It looks like for 0, 0, we'll plug that into our line. We get 0. Is that actually greater than 0 minus 2? Yes, it is. Okay, so because our inequality is true on that side, we'll shade on that side. And now the solution to the actual system of inequalities is going to be the region that's double shaded. So that would be, let's emphasize it, be this region inside the parabola to the left of the line. There we go. Hopefully that helped explain how to solve these nonlinear systems of equations and inequalities, and I'll see you guys next time.